Uh, Tracking. Maybe it just takes a little bit of time. Still not seeing us live at the moment. Refreshing the page. Yeah, we're live now.
Oh, perfect. Okay, hello everyone. Welcome to today's episode of Quirkcast. I am your host, Tim.
Yeah, Mikey.
And I'm Sahil. Welcome everybody to a brand new, exciting episode of Corecast. We're back after a 2-3 week hiatus due to scheduling issues, but glad you all could be here with us. Before we get started, a few logistical things. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this every Tuesday, 5 p.m. Pacific, 8 p.m. Eastern, do ask us questions during the episode, and we'll get to it. So without further ado, let's get to it. So Tim and Mikey, this is a interesting question I've wondered for a while, and let's just start off with it. What happens before the Big Bang? Tim, let me point this question to you.
Yeah, I would say this is definitely a question that physicists have wondered, and it's a natural one too, because when we think about creation, you can always keep asking the question. When we have the Big Bang theory, this is what created the universe. You can keep asking the question, well, what happens before then? And you can argue that if we have an answer for that, there's always going to be more question. What happens before then? Then what happens before then? But one thing to keep in mind is that when we ask the question, what happens before, we kind of have a notion of what before means, because in this universe, there's the before and after, and that's in reference to time. But it gets tricky when we talk about what happens before Big Bang, and that's because the universe hasn't even fully formed yet. So the notion of time isn't necessarily well defined, but of course we can still talk about it, and in some ways the question, I think it's more associated with like what sort of set up the condition for Big Bang, like what sort of created the conditions for Big Bang to happen. So physicists have definitely thought about this, and depending on how far you go back, minimally before Big Bang, there's got to be a period of matter creation. And then what happens before then, it gets more and more speculative, right? So matter creation is definitely one portion of it. But what happens before then? And this is where the idea of inflation comes in. And it's a guess. It's just a speculative guess on what happens. And it's actually quite reasonable. But the thing is, once we step into this idea of inflation, so basically slowly you take a bigger and bigger leap of faith, and then ultimately inflation will lead to this idea of the multiverse. And then we'll describe that a little bit later. But once we go to the multiverse, we walk further and further away from science. And the question a lot of physicists is asking is, well, is this a scientific question? So the line becomes a little bit more blurred. So the answer is very, I would say, nuanced. Yeah.
Yeah. Anything you want to add to that, Mikey?
Yeah, I mean, maybe it's like, I don't know, I feel like this is like a lot, this is a response kind of based on my personal experience, but I feel like this is the question, like a very natural question to ask, right? Like that annoying kid who's like, why? And then like you say something like, why? And then you can always ask why, right? You can always like, dig deeper and deeper and deeper. Um, um, and the standard answer, like when I was coming up, like everyone always answered this question the same way. Well, you ask what happens before the Big Bang. Well, the Big Bang is where time was created, so it doesn't make sense to ask what came before, because and there was like, oh yeah, you're thinking about it wrong. Like you can't ask before because this is when time was created. Um, and I don't know. Looking back, I feel like that's kind of an answer that it seems like it makes sense at the time. but it does lack a little bit of creativity because you can still think, as Tim mentioned, you can still think of mechanisms for what could give rise to the phenomenon that we see as time. And I feel like people who said that were just kind of avoiding a difficult question at the time. Because certainly you can, you know, we can imagine scenarios where something like our universe could have arisen, you know, through some other means, or like we understand time well enough to, you know, begin to think about how it could have been created. So I don't think we're limited by this idea that, oh, you can't ask the question of what happened before because, you know, time didn't exist before then, so it doesn't make sense.
I guess so. One thing I want to kind of, I mean, this gives us a lot to talk about. So the first thing I want to focus on is like this notion of time, like before, like Big Bang. It doesn't make much sense. I mean, what does it mean to like create time? Like, why can't you just naively say like, oh, I'm just going to call everything before the Big Bang like -1 second, -2 seconds, just use negative time. Like, what's the issue with doing that? Just to really like hone in on this.
Yeah, I think the problem is
Yeah.
time. Yeah, time for us is what we observe, you know.
Mhm.
But as we know, as we go before back in time, the universe gets small. The universe gets smaller and smaller and smaller. Even the notion of time gets smaller and smaller and smaller. So sure, you can loosely talk about the abstract notion of time, but
Mhm.
like just because there's a time in an equation doesn't necessarily mean that that time is actually meaningful in that way. You know, like
What does it mean what we are comfortable with thinking it means?
right, like now, of course you can talk about it. You can say, hey, it's like if you look at numbers, right? You can look at 1, 2, 3, 4, 5. Well, let's go to 1, 0, -1, -2, -3. You know, you can try to do that. There are mathematical equations that tries to do that, but it doesn't necessarily mean that they are meaningful. They are like physically meaningful. So yeah, so we could talk about it, like you said, just you know, get the number, send it to negative, but it doesn't
Yeah,
always make sense. That's just something we have to keep in mind.
I see. I see. And then the other thing I'm wondering about is you mentioned like there's the Big Bang, and then before that, there's some notion of matter creation. But couldn't you say that they're the same thing, or are they not the same thing? Can we
Well,
clarify
matter
that?
creation
Like,
happens after the Big Bang, right? According to our
I I.
uh,
I think the line is a little bit blurred now because there's no good
mm,
definition on exactly when Big Bang happened.
or a good
Um,
mhm.
definition of what quote unquote matter. So,
yeah. I mean, this line is blurred. It just where does the standard theory end and the speculative stuff begin, right? But okay, so I think experimentally speaking, we know that the universe was harder and smaller at some point relative to today, you know, and denser. If you extrapolate back, there was a moment at which probably hit a critical density, you know, some critical temperature. It was as dense as possible. You can argue that, well, if you say that's the end of Big Bang, what happens before then those conditions need to be created. And then generally we believe there's a period of what we call the reheating, the heating up of the universe. You could include that to your standard Big Bang theory. I don't think it's too controversial, or
wait,
you
I
don't
think
have
we
to
should back
include
up a
it.
little bit because, you know, like, okay, so now we're talking about like a proper definition. Like, I think when a lot of people think of the Big Bang, they like a lot of people talk about this idea of like the singularity, right? Like everything exploded from one point. No
Mhm.
one really believes that's true these days, right?
Yeah.
Really.
There is no singularity. A singularity is just if you extrapolate in a very dumb way, you get infinities. We know that infinities don't necessarily exist. So infinity is just an indication that, hey, look, you couldn't extrapolate. It's like if you type into a calculator, you know, you type in a number that's too large, the calculator errors out. You know, it's not like
Mhm.
you couldn't multiply numbers that large. It's just the calculator couldn't handle it. It's the same thing. If you extrapolate back in time in your equation, you hit a singularity where things are infinite. It just means that your physics is bad. Like the
But
universe.
maybe we should think about this in terms of like myths to debunk. I feel like this is one of the things that I was told like early on when I was studying physics is like, okay, the Big Bang is a singularity, and so time doesn't exist then, so it doesn't make sense to talk about before. Um, and I don't think anyone sensible believes that's true, right?
Right. Yeah.
So the idea that the Big Bang means that the universe came from a single point, like, let's not think that. We know that the universe was smaller, we know it was hotter, but there are people out there who would extrapolate that all the way back and say, okay, that means the universe must have come from a single point that was infinitely hot, which is obviously a silly thing to extrapolate from the simple observation.
So then could you guys, I mean, in like maybe one or two sentences, define what Big Bang actually means? Like even if it's not a well-defined time or, just like what is it generally?
I think most reasonable people study cosmology would right now would say that the Big Bang is defined as the idea that the early universe was small and hot, like independent of like what you mean, like small relative to what or hot, like, but
Yeah.
it just means that the universe came from a small hot um origin.
I would say, if I were to write a paper, I would say the Big Bang begins when the universe reached a maximum temperature, the maximum hotness. That's when the conventional Big Bang begins. And that's, I think, not too controversial. And you can debate how hot,
Wait, so would that be the point of reheating?
like after reheating, basically. Yeah.
Okay.
After
Oh,
it heats
okay.
up.
Well, okay, but see, most like I feel like casual science fans, that is not what they've been told.
Yeah, of course not. Yeah.
Okay, so Tim, based on your definition, what the question we're actually trying to ask, and we can discuss maybe other ways that it's ambiguous, but we're essentially trying to ask what happened before the universe like reached, I guess not reached, but like was at this like maximal density, like maximal temperature,
Wait,
and
no,
then
if you
uh,
define the Big Bang the way Tim defined it, then the
uh-huh.
answer is kind of boring because he's defining the Big Bang to be like after. So then it's like, okay, then there's clearly a history before that, and it's not as controversial, right? If you define the Big Bang as the point of reheating, then clearly there's a history before that.
I guess could we also define what reheating means? It sounds like, I just took this like big ball and I put it in an oven and I just like reheated it like from the freezer. Like what does
It's not
reheating
far from
mean?
the truth. Well, yes,
Oh,
it's the idea of how matter got created. Yeah, like because the first universe was just a big ball of pure energy, and then
okay.
yeah, and then as you described,
Yeah, I mean,
got put in the oven, and then matter came out.
it's one of the most basic requirement for Big Bang is that there need to be stuff. I think it's not very
Yes,
Okay.
stuff
controversial.
needs to come out. Stuff needs to
Yeah,
come out of it.
yeah,
Mhm.
but it's still not totally solid because we don't know exactly when the era of reheating happens. We don't really know how hot the universe got. There's some estimate, right? Maybe it got as hot as somewhere around the Planck scale where quantum gravity becomes important, or it could
Mhm.
be a lot lower. So there's a huge range of possibility. So that part is, I think, up to debate. You can write papers about it. How hot was the maximum density and temperature that the universe achieved, right? You can debate about that, and then you can go backward more. What created the condition for the oven to heat up? What dial up the knob? What caused the dialing up of the knob? Now that's one
Mhm.
step more removed from concrete evidence and more
Mhm.
speculative territory.
So what you're asking, Tim, is like what essentially created the conditions in which then you could have a Big Bang? Is that what the question is?
Yeah, it's basically keep asking this question, right? Like it's like, oh, what happened
Mhm.
before the Big Bang? Well, the minimal requirement is that there's need to be stuff in it. What created that stuff? Well, there's some kind of reheating. Things heat up. Well, what created that heating? You know,
Mhm.
you can answer that question and again and again and again.
Mhm. So let's actually go down that train as you're mentioning,
Yeah, let's
and
do
we'll
it.
get to the point where we can't like eventually answer as we'll discover later in the episode. So let's start off with like I guess Tim, what was the first sorry, you mentioned a whole bunch of questions. What was the first one that you mentioned?
Yeah. Well, in order for Big Bang to happen, there needs to be
Hmm.
stuff for the bang, right? If there's nothing to Big Bang, There's no Big Bang, so there need to be matter and energy. So you
Well,
can
no,
ask.
there needs to be a background first, right? That's the first thing. You need a background on which
Sure,
matter
you
and
need
energy can
background and
even propagate
stuff.
across.
Yeah,
Yeah. So
yeah.
how do you create a canvas to paint on?
Yeah, I guess Tim, I'm gonna point that question to you.
Yeah, Tim, how do you make a canvas? I want to
Well,
make a
I mean,
painting. I want to paint the universe. How do I? Where do I? Can I go to like an art supply store and you just get a canvas?
I mean, the canvas is just Einstein's theory of relativity, right?
The
It's the
canvas, it
space.
makes itself, right? It makes itself. The universe makes its own canvases.
Yeah, I mean
That's
that's what's
cool.
interesting about it. I don't think it answered the whole question. It doesn't answer how it was created, but the theory of relativity tells you that the space and time are malleable. They can be stretched, right?
Space loves
Mhm.
to make canvases.
Yeah,
It just likes to produce
Mhm.
yeah.
backgrounds on which things get.
So it's natural to say that, hey, the canvas was created by gravity, meaning that
Mhm.
the canvas was maybe a different shape, smaller. It got stretched and molded by gravity, and then so that creates the canvas. And you can ask, well, what's the paint? What's the substance? That's the matter. That's particle physics. So there's got to be some kind of energy stored in something, right?
Mhm.
So
But
there's some.
making the canvas is not that, it's not that trivial, right? Making the canvas is tricky. You
Yeah,
have to like
but
you have
we
to
have
have
to
neighboring points talk to each other and be correlated.
save that for later because it goes in
Uh,
steps, right?
okay, okay,
Because
that's
the
Mhm.
I would say the canvas itself is more primordial. It's something that's more
yeah, but
ancient.
that's why it should come first, right? We can agree to
Well,
disagree.
we're kind of working backwards, chronologically backwards. So there's
Oh,
stuff.
okay.
Yeah. Let's kind of go backwards because
Bottom
I want to
up,
see
not
how
top
far we
down.
can push this.
Okay,
So
okay.
okay, so stuff. So that was from some ball of energy, or how would you describe it, Tim or
Yeah,
Mikey?
generally there needs to be some energy stored somewhere for stuff to get to get created. This is like your
Yeah, if we're
ingredients. If you
working backwards, right? We see that there's stuff now, and
Mhm.
one really easy way to create stuff is with friction, right? You just rub stuff together and sparks fly out. That's one way to get stuff. So maybe that's how stuff got here.
well, I mean, in particle physics, we have a generic concept called fields. I mean, everything's a field.
Mhm.
Like if you turn on your oven, the energy comes from electricity. You can argue that the oven heats up because there's an electromagnetic field ultimately, right?
Mhm.
You're paying electricity bill if you turn on the electric oven. There's kind of an energy field storing that electricity, and that got turned into heat. And it's similar to in particle physics. And now it varies from theory to theory. The leading theory, inflation, will describe why it's the leading theory. Propose that there's a field called the inflaton. It's kind of the, I don't know. It's like the electricity utility company of the universe. It was ready, and then slowly it's able to heat up the oven and get stuff created. And if you go to other theories, other more fringe, less mainstream theory, that energy could come from. I think there was the brains colliding, some string theory things,
Mhm.
or come from other sources, right? But there's need to be this. The energy has to store from somewhere. I think it's safe to say that it comes from some field, probably.
Yeah, those are
Mhm.
basically the same idea though.
Similar, exactly.
Yeah.
Okay. So there's something maybe inflatons. We can talk about that in a little bit. Actually, we did a previous episode on inflatons. So anybody interested in that topic can check out that past episode. We definitely dig deep into that. So I guess I don't know whether it makes more sense to stop on what inflation is, or if we can explain like this canvas part and then jump to inflation. I
I mean,
guess.
it's kind of the same, right? So inflation
Mhm.
is like a mechanism for. It's not like, I don't know. Like it's kind of like poetic when I like used to ask what happened before the Big Bang, and they're like, don't ask the question, it's stupid. Time was created, or space was created too.
Mhm.
Um, but does I think the question, does physics have an idea for how space and time can be created?
Hmm.
Um, and I think inflation is the answer to that question. And I think that's what makes it kind of special.
Yeah.
Um, yeah.
So
Yeah.
And the
So
fact that
real,
it's like so easy. It's like it doesn't, it's not difficult to do this. Like the universe wants to make space, it wants to make time.
so I just want to ask real quick. We're talking about creating the canvas as you were mentioning
Yes.
before, right? Okay.
Yeah.
Okay.
Yeah.
Tim,
Yeah.
go ahead. You were about to say something.
yeah, I mean, one of the problem is we're not just talking about any canvas. We're talking about a very unique canvas that is our universe. And
The
and
best
and
canvas.
and one of the most important properties of this canvas is that it's big. I know it's like a very dumb thing to say, but like the universe is big, it's not small. And it's actually not
Mhm.
obvious how to create a canvas that big, you know,
Yeah.
or had the
And everything's
potential to get
stretched.
that big, right?
Yeah.
So, and we know that because quantum physics is very important in our universe. It's the fundamental laws. Everything's quantum mechanical, and you know that quantum mechanics deals with very small stuff. So this naively, this seems to be like a contradiction. The universe is so big, quantum physics is so small, right? If you just flop quantum physics on a very large universe, it becomes a very violent universe because quantum physics is very violent. So if you have violence everywhere, you know you're gonna do violence to the universe. So
Ah,
what happened? One of the requirement of the universe is that it's a very nice canvas to paint on. It's very uniform. It has very little violence, so that things can build up. Like
it's
it's
smooth and
yeah,
stretchy.
it's very smooth, and we all have evidence that it's very correlated. Um, so the only way we know correlation to get generated is through quantum entanglement. Um, but then you know that quantum effects occur at a very small scale. You know, like we don't usually observe quantum mechanical effects. Like my left hand is not quantum has no quantum mechanical relationship with my right hand. I mean, they're synchronized in my brain, but like there's no quantum mechanic business going on, right? But in the universe, we see that there is quantum mechanical business going on from one end of the universe to the other end. So physicists were very puzzled, right? Like the universe is so large. How the hell does quantum mechanics have anything to do with it? We see that in the data, roughly speaking, in the looking at the plasma imprint of the early universe. So one solution is that the canvas got really big really quickly. So the quantum mechanical picture, I guess, got like stretched out. So that's where the idea of inflation comes from, is to build that canvas that matches our universe.
Actually, Tim, could you spend maybe a few moments describing like what do you mean that one end of the universe is correlated with the other end? Like what evidence do you see like that? What does it mean for them to be correlated?
I think there are two parts, right? First of all, if you look
Mm,
at different directions in the universe, they look very similar. Like you see
mhm,
stars on one end, you see stars on the other end. Like if you, I don't know,
mm,
And the
if
same
you
number of stars.
roughly speak, statistically they're similar. So like if you're
Shockingly similar.
yeah, if you're in United States versus if you're in Australia, the sky statistically looks similar. But it's more than that. There's actually what we call cross correlation. If you what's the probability of stars in one direction? If you look at that, how that links to the opposite direction, there is some correlation there, or like at different angles. This is a little more abstract, but like statistically, they are
No, this used to
linked.
bother. This used to like. This was not intuitive to me. I remember this really confused me when I was like starting to study physics because people would talk about like this as though it was a surprising thing, and I couldn't see it. But it kind of says, okay, so imagine I look in this direction and I count how many average stars are there in this cone, and I count. Oh, there's an average of like 9,664,000, like some very specific number. And then I count the number of galaxies in this cone. I see it's exactly the same in this cone. Every cone has almost exactly the same number of galaxies. How is that possible? It's like almost like exactly to the exact same number. Like it's a very surprising and shocking fact about the universe, and I didn't appreciate this for a while, but like you have to explain that. If this part of if you look this way and it looks the same as this way, so like one part in a million, there must be some shared history. How could that just happen by accident?
I guess one question I want to ask is like what you seem to be describing is uniformity. How
Yeah,
is that related to correlation? Like, why is it that it just, I mean, does uniformity imply correlation, or I'm just trying
yeah,
to relate these two
sure.
concepts together?
Yeah, because like uniformity means sameness, and sameness requires the two things
Yeah,
are
yeah.
the same.
I mean, it's more than that, right? Because
Mhm.
yeah, clearly we could have easily imagined a universe where there are way more galaxies on one side versus another. Like that wouldn't be a
Mhm.
crazy universe. That would have been
Yeah, like
okay.
there's way more clouds in this direction than in that direction. Like that's more like
Yeah,
cloud
exact.
coverage is not uniform at all. Like it'd be crazy.
Right, exactly. Yeah, like that's a great analogy. I think like the weather right now in the United States is different from the weather right now in Australia. Like that's, but
Mhm.
somehow the galaxies look like the same, statistically the same
Yeah,
as the
what if they were to,
galaxy.
what if the US and Australia and Sydney, Australia were exactly the same temperature up to 0.000000001%? Like you'd have to explain that. Like,
Yeah.
how is that possible?
Yeah, but I think it's more than that. So the statistical average are correlated, but it's beyond that. It's the fluctuations. It's a little
Yeah,
harder to describe.
that's
So
true.
it's more than that. It's like, hey, if there's a cluster of star here in this direction, it enhances the probability that in a different direction has stars there according to some formula. And this is, you can go
Mm.
into details. This is the power perturbation spectrum. I don't remember what's the name of that. There is a correlation depending on how large the angle is. That correlation goes up and down in like a wave, you know.
Mhm.
And there's no other way to explain it. Like, why is there a statistics that looks like a wave? The only way that happens is quantum physics.
Oh, it's a way with just constant.
All right, so we've described like essentially inflation as the idea that originally the universe was smaller, and so I guess quantum mechanically things were entangled with each other, and then or correlate with each other, and then inflation just sort of like just made it get much bigger.
So entanglement and the idea of a correlation, they're not directly related. I guess we're
Okay.
gonna relate them later. But yeah, so inflation is just this idea that if empty space has energy,
Mhm.
it blows up. Like
Yeah,
just if you just put a ball of energy in space, that ball of energy
Mhm.
will cause the space to just explode and blow up like a big bang. So
yeah.
it's very easy to imagine a big bang. All you need is some constant energy density in the universe, and then big bangs just happen everywhere all the time.
Hmm. Okay. Okay. So is it fair to say that could you say inflation and Big Bang are like the same thing, or are they not the same thing?
In my mind, they're the same thing, but I guess I'm
No,
like a new school. Like
no, no.
game someone or like, well, I mean, no, like old school physics look oh the Big Bang. Like, who really knows what the Big Bang means at this point, right? It's
So, okay. So technically, that's definitely not the same thing because there could be
Okay.
universes. Technically, you can have universes with just inflation, no Big Bang, because
okay. How
you can have a canvas that keeps getting bigger and bigger, but nothing.
that never reads.
Yeah, then nothing gets produced. That's possible,
Okay,
right?
that's so semantic. It's such a
Yeah.
technicality.
Or no, no, but you can also have universes that just
Okay, it's not
reheat.
technically. Yeah,
You can have
yeah,
universes that just reheats, but like
yeah.
it doesn't expand in that way. So you'll never get a ever expanding canvas. So, but generically, I would say generically, if you were to like randomly pick a universe, chances are there's gonna be like a canvas that's forever getting bigger and bigger and bigger. And because of the quantum mechanical nature of things, you have little spots that get that blows up, that creates you know, you can have a little spot that blows up, and then things get created, and you can have universes forming left and right.
Hmm.
I see. Actually, so now it seems to be like you're nudging at the idea of multiverses. in the sense as the difference between like when we say, oh, there's a universe that exists that can only have inflation, but no Big Bang, and to draw that distinction between them. Is that fair to say?
Yeah, I think there's
inflation predicts the multiverse.
Yeah, I would say that that's true because generically, because we remember this, the only reason why if you believe in the inflation model, it's an explanation on why one direction in the universe looks the same in the other direction, right? It's because a really small patch of the universe got exploded really large very quickly, But if you accept that fact, then you can ask the question, well, hold on a second. If one tiny piece of the universe is able to blow up, why can't another part blow up independently?
Yeah.
So the correlation has a limit, Like it's not infinite. It's not like everywhere in the universe it should be correlated because that doesn't make sense. There's nothing infinite about. We don't believe in infinities. So if you believe in the theory of inflation, you're saying that hey, like one direction one direction in the universe looks the same in the other universe. It's because it got inflated very large, right? But there's still a boundary. There's still a limit in that inflation. It's very, very large, but not infinitely large. So so you can either believe that only happened once, but I don't think our universe is that. It would be crazy for it to just happen once, right? If there's if there's enough condition, if the conditions are right for it to happen once, why not again?
Yeah, it turns out if you're trying to think of a mechanism for creating a universe, it's very difficult to make it stop after one.
I see. So are you saying like basically that there, I mean, so okay, I want to think how to visualize this for like in my mind. So I'm imagining that like you have the universe as this like really dense hot ball of mess, and then inflation just like expands it to no end. But like where does that dense ball, I'm gonna say ball for lack of better words, fit in with these other universes that you might be talking about, or other patches of universes that might expand? Or is it like that one part of this dense ball expanded, which gave rise to our universe, but another patch, maybe like really far away, also expanded, and maybe at a different, I'm using quote time, for instance. Like how do I think about this?
Yeah, the thing is, like, if you give me one universe that's very large, there's no reason why one location is related to a different location. Maybe if they're close enough, they will be related. But if they're really far, Einstein's relativity says that 2 points are only linked if one can send light signal to another, because light signal travels the speed of light, But if 2 points are really, really far away, there's no reason they're related. And that's before inflation, right? So, and then you say, well, hey, look, by chance, like location 1 happens to, because quantum physics is all about chances. Location 1 just suddenly exponentially get bigger. Location B knows nothing about it. It might decide to also exponentially get bigger or not. They don't talk to each other. So it's a kind of like, I don't know, it's like fruits on a tree. You have one fruit coming out, that's one universe. You have another fruit coming out, that's a different universe. They don't talk to each other.
Okay, that makes more sense. And so when you talk about multiverse, we're not talking about like the quantum mechanical many worlds. We're actually talking about like physical like universes that are just causally disconnected from each other.
As far as I know, these are two completely separate concepts.
Okay,
I'd like to talk
I just
to
want to
someone
make
who
sure.
thinks they can relate to. I don't know.
I think they are somewhat related, though, I would say.
Are they? I've never heard someone not crazy say that, though.
I mean, like if you think of the entire multiverse as one giant, because previous episode we talked about what the universe is computing. You can argue that the entire multiverse could be computing.
So is the landscape like an amplitude then?
That's probably not well defined, I would say. Maybe not. But it just there's a quantum mechanical object, right? and one
Mhm.
universe is just one part of it turned into a universe. Another
Okay,
part
yeah.
of this thing could be a different a different universe.
Okay,
Like,
yeah.
yeah,
It's a superposition of possibilities
right,
like in
right,
space.
yeah.
Yeah, okay. Yeah,
It's
okay.
it's 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 kind of crazy to
Fair enough.
imagine the entire universe could be in the superposition of uncountably many universes.
It's
We live
very
in
against the
one.
human ego to think that way.
So, what you could say, so now, so I guess like coming back to the original question of what we started with, what happened before the Big Bang?
Ah,
You
yes.
mentioned inflation. So inflation helps you create this canvas. But I guess like I mean, can we talk about like what happened before inflation, or like does that even make sense, or where are we
That's
going? Is like
You
I
can certainly make a model, right? So you can ask like, well, I think if you say the question doesn't make sense, it just means you're lazy and you're trying to like shut someone up who's asking you a question that you can't answer. Because it's just easy to say, oh, this doesn't make sense. Um, but certainly you can think of a model to explain how this could have arisen. Like for example, Sean Carroll has written down like models for inflation where you just imagine that you have like he just actually imagines the simplest version of a quantum computer that starts out with like a bunch of bits that are like in a like a 0000 state, and you just run the tape forward and you imagine that like this computer just does like it just basically isn't doing anything except random thing, and it looks like the creation of the universe because like the parts of the computer interact, and then that creates connections between neighboring points, and it starts to look like space. And so, like, can you write down a model that looks like an inflationary Big Bang? 100%. Yeah, if we had quantum computing technology with error correction, we could easily simulate a universe or the creation of many universes um, on it. So
yeah,
what happened? Like, yeah,
but I would say like an explanation like this,
yeah,
because you can ask the next question,
which
what before then?
yeah,
If it's like a
sure,
computer,
sure.
who turned on the computer?
I would be satisfied with it. Like if someone told me that we were in a that that inflation is true and that inflation is driven by some quantum computational simulation, I would say okay, we got the answer. I would
No,
be
but
satisfied. I wouldn't have to go deeper than
I
that.
think that will still be a question, right?
No, no,
But
you're right. You're right. No, but that's the point at which I would give up. I would be like, okay, I'm satisfied with this
I would say
universe.
the more mainstream answer is the eternal inflation idea.
No, sure,
Mhm.
eternal inflation, but you can simulate eternal inflation on a quantum computer. So are there like beings that are simulating eternal inflation on some kind of like laptop?
Well, I don't think you can quite simulate it. Well, I mean, you could try, but
You
eternal
could,
inflation is
totally.
this idea that there's no beginning and no end. It has always happened. Like,
Sure, in a computer it would look like that.
no, but you still have to pick a beginning in a computer, right? You have to pick a beginning.
Yeah, well, okay, but then now we're getting into like speculations about what these godlike beings might have intentions might have been for creating this computer, the simulator, or and I
But
feel like I can't
But
answer those questions, but
one thing to note is that like when you have a computer and you talk about like transitioning states, that implies some, maybe not what our notion of time is, but implies some notion of time. So it
yeah, there's
implies that
clock time.
there's some
Yeah, there's a
like
clock time.
beginning and some what?
Yeah, there's a clock time on the computer, right? Like how many computations it
Yeah.
performs. Yeah, there's a very
But
similar notion in the idea of like simulated universes. That there's like the universe can do a certain number of computations per second,
Mhm.
and that kind of defines um, you know the march of time in terms of
I
there's
guess, Tim, can you dig a little bit deeper into what eternal inflation means? Is that the same as the inflation we've been discussing, or is that a different, like, souped up concept of inflation?
yeah, I think well, eternal
not more
inflation
souped
is.
up because it doesn't require more machinery. It's just a natural consequence, right?
I think it's just a realization of typical inflation
Yeah,
model.
it's a
People come up,
realization.
yeah, people initially build these inflation model that says, hey, the universe could balloon up, get stretched really large, and then it can reheat. The Big Bang could happen. They just realized that if it can happen at one point, it could happen at different points.
Eternal inflation is like, oh wait, it can't just happen. Well, we can't stop it from happening. It's gonna just keep happening.
Yeah. So
could you say? Oh, go ahead, Tim.
Yeah, I was just gonna say yeah, and then people add the eternal label to it to say that it didn't. There was no point at which this process began, and there's also no point at which this process is ever going to end. It ever has been, and
that's kind of funny, right? They were like, "Oh, this is possible," and then they're like, "Oh, it's inevitable."
Yeah. So okay, so what you're saying is like, I guess, but couldn't I ask the question like, if so, just what eternal inflation says is that like the, I guess just this, I don't know if I want to say object, but this multiverse or this object existed, and then inflation just happens at like arbitrary like times, or I don't even know what word to use, but I'll say arbitrary times for lack of better words, at like different parts of this like this very complex object, and one part of it gave rise to our universe. So essentially, like, eternal inflation is a mechanism of universe creation. And then, as Mikey is saying, it's like once you create one universe, it's hard to justify like why couldn't you create other universes? Am I understanding that correctly?
I would say that's absolutely accurate. Well, okay, the one thing I would say is that it's not eternal inflation is the idea that you have this energy density in the universe. And Einstein's theory says if you have an energy density in the universe, it causes rapid exponential expansion. And eternal inflation, like, I think it's Tim was saying, it's the realization that if you combine this with quantum mechanics being the idea that like no two things can be like completely simultaneous, there's like randomness, like, then you automatically have the situation where you can't synchronize how things are going to blow up, which means that things have to blow up independently, which means that you have to have multiple independent universes.
Okay.
I can't think of a logical way out of that.
Fair. So we got an audience question that says, can you address the concept of how there's no center of the universe? And is the James Webb Telescope only limited to certain areas of the universe closer to us than 300 million after the Big Bang? What is the limit?
Yeah, it sucks. I mean, we're trapped in the perspective of our own point of reference. So yes, the James Webb Telescope is trapped. We're trapped in a box because we're sitting here and we can only see out from the center here. But it's actually a myth that there is like, so the universe does have a reference frame, right? Like Tim could probably speak on this better than me, but I remember that's like people always tell you like, oh, like relativity says that there's no.
Yeah, only on average. Only on average.
Yeah.
And this average is like an alien and us might not even agree on exactly. So only approximately.
Yeah.
So yeah.
The universe does have a rest frame though.
Sort of, yeah. But when we talk about the multiverse, there probably isn't one. The reason why the universe has an average rest frame is because our observation is limited to our own observable universe. And we're limited to parts of the universe where light have some way of communication. And because of that, there's a notion, you can kind of cook up this notion of an average reference. It's because they are connected in this way. But if you look at generally very, very far away universes, that doesn't need to be the case.
In fact, the idea that there is such a thing as an objective perspective on the global universe seems to be looking less and less sensible. Like the idea that it doesn't make sense. Like every single observation in the universe depends on your relative perspective. So I guess in a sense, I feel like in a sense Copernicus was vindicated. We are the center of the universe, just not in the sense that we thought we were, but everyone is at the center of their own universe, and there is no objective universe aside from the one that you yourself are at the center.
I like that seems very poetic.
It's weird. It's weird that that turned out to be the case.
I guess so I guess coming back to our the question that started this. So Mike, you proposed that like you'd be satisfied if the answer was like, oh, it's some quantum simulation and some computer that was just there
Okay,
since the
I'm
beginning
not
of
trying to get
time.
religious. I'm not trying to get religious, but if someone could just come to me and just give me the answer, and they were like, "It's God. There is a God, and he just made it this way," I'd be like, "Okay, well, I guess I can't really like ask any questions beyond that because I'm not gonna like try to get to know this dude and try to understand his motivations." Like, that's I feel like that's the point at which I could like lay my sword down to rest and just uh, retire, thinking I got to the end of what's possible to know.
Fair enough. I guess Tim,
Yeah.
what would you say like now that we've kind of like gone to the I don't know, maybe the end or
Edge of what's possible
with
to know.
eternal
Yeah, Tim, I
inflation,
want to
there's
know
no
too. I want
end.
to know how you feel about this.
I mean, I think there is no end because we're always gonna hit this.
Until we are the gods that create the universe, like in
No,
Interstellar.
I think we're always gonna hit the boundary of scientific knowledge. You know, like you can't avoid it. In some sense, like you can't get something out of nothing, right? Like if you keep asking back this question, like what do you expect? There's always gonna be some answer. The only answer that will satisfy you is that there's nothing. Nothing created something. That just is not possible. So eventually, I think we're at this natural point where you ask these questions, and it becomes less and less science, and that line it's not sharp, you know, depending on how you enjoy where you draw the line, what's scientific, what's not. We're always gonna have this ambiguity. Like,
Wait,
hey,
is it less than the science, or does the science just become more challenging? Which I guess you could argue that that means less scientific because those things become less experimentally accessible. Then I don't know, maybe you can argue you're not doing science, but I mean, so it's like I feel like it's just a victim of its own success, right? Like we're asking questions
no,
and
right, but I mean, there's the problem that we only live in one universe. We cannot sample
yeah,
other universes, and if we
yeah,
believe in quantum physics, we only are sampling part of this amplitude. If an amplitude even
sure.
makes sense,
But
there's a
I feel like that's simply the fact that we can even ask that question is a testament to the success of you could pretty much come to the end of the road if these are the questions that we're wrestling with.
I guess Tim, I would pose this last question to you to kind of I don't know, like you know, force an answer out of you if possible. But given internal inflation, like would you say there's anything like I don't even know if you can say before, but like what would give rise to the condition of eternal inflation?
A quantum computer that someone built. That's one example.
it's just more eternal inflation. It's just more.
Yeah.
You know,
So
this
if I
is
keep asking you what was there before, you just keep saying more eternal inflation.
I mean, the algorithm for eternal inflation is not that complicated, just like strictly speaking as like a physics theory. Um, so
maybe there are other types of eternal inflation lead to that one eternal
sure.
inflation. It's just
Yeah,
layers and layers of eternal
yeah.
inflation. I don't know
Who
what
knows?
else.
Maybe our internal inflation is like one Python program and there's a whole like language of other like, you know.
You know, Tim, your answer reminds me of that story of its turtles all the way down. Just greater and greater inflation the more you go down layers. But yeah, so we're almost at time. So I wanted to leave you guys a chance to, you know, in our tradition, leave with the audience with any words of wisdom that you learned before the Big Bang.
Yeah,
Yes.
I think for me, like this question is like, I don't know, I guess kind of personal because I feel like okay, so who knows what happened before the Big Bang? Who knows how space and time were created? But I think we're at a point right now where we're starting to be able to imagine how you could do it. Like we can imagine a computer program that can make eternal inflation happen. It can make the universe like on, or maybe you could argue it's not real, but like we can imagine how to create something that would make us here to ask the question. And so that's kind of cool. Because that's it.
I would say, well, let me address one audience question I think earlier about dark energy. You know, I'm not going to describe, recently we have some hints that dark energy might be changing, but
What?
yeah, the date, yeah, but we'll talk about that later. Recently. But that's besides the point. So yes, eternal inflation is driven by dark energy. I guess you could call
Kind
it.
of dark
It's
energy.
a dynamical
Kind of
dark
dark
energy.
energy.
So
No,
so
it doesn't. Well, it just, but yeah, some kind of dark energy. Yeah.
yeah, so I would say like yeah, we don't have evidence for inflation directly, but just the fact that we observe dark energy, we know that the exponential inflating universe is
The
plausible.
mechanism is confirmed.
Yeah, the mechanism is confirmed. So and it's crazy that such a simple mechanism could explain so many things about our universe. And
It's rare when it happens in physics, right?
it's
When you
true,
come
yes,
across a theory
yes.
like that, it's like, wow, it's actually easier than we thought it was, not harder than we thought it was.
But indeed, it's and that's one of the reasons I did in my scientific career I did not work on things to do with inflation, is because it's a complete black hole of like physics turning into metaphysics, because this boundary between what's scientific and what's not just is
scary.
completely blurred.
No, but it's amazing that science has advanced to the point where it's becoming blurred. That's crazy. That's a success story.
I mean,
It's like almost like becoming superhero status. Like you're not even like asking normal questions now. You're asking questions that no one would ever even imagine would be possible to answer.
but I mean, a big part of it, we'll never know the answer. So I guess this is part of life,
No, I think well, okay. I think that this is a argument for why we should adopt, like, I'm very against the idea of, like, or the traditional idea of faith, but the idea of like theoretical evidence. Like, okay, like you can't show it in front of my eyes. Well, what does that really mean? Okay, you can't shine photons into my retinas that convey this information, but there's other ways to infer the correctness of things, and I don't know. I think we're better at it than
but
people like to give us credit for.
I would say I'm happy with the ignorance. I know that part of this question has stepped outside of scientific boundary. Practically,
Well,
perhaps
we know the answer, right? And we're comfortable with it, even if people don't believe us.
a
Like,
plausible
people
answer.
think, oh, no, people just say, oh, that's just your theory. It's all theoretical, right? But they don't understand, like, yeah, but that's not that is significant.
Sure, yeah.
There are real reasons for thinking that this is okay. We don't have any experimental evidence, but I'm still right and you're still wrong. So.
All right. So I guess Tim, I guess that ends your answer.
No, I wasn't talking. I wasn't pointing that at you. I was pointing that at like other people.
All right then. Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah, see you all.